לחצתי. מי שיודע לא רץ להראות שהוא יודע. אחלה. עוד לא רואים את המסך אני חושב, אבל עכשיו יראו. ואני אספר לכם על למה אני לא אוהב זום. זה קשור לפשלה אדירה בקואלקום, באיזה וובינר. פשלה היסטרית, לפני איזה כמה שנים. הרבה לפני שזום היו כולם. ופשלות כולם אוהבים לשמוע. יאללה. יופי. אז אנחנו פה, והפוסט המדובר הוא... ראיתי אותו לפני רגע. אופה, איזה אלופים, רואים? לבקש עזר. אז זה הפוסט המדובר, טה. הנה החברים שלנו, עמיתה ויואב, ויאללה, תעשו שרים ותחציצו, תשתפו מה שאתם רוצים, ובכיף ובחב. על הכיף כיף. אחרי שעשינו עוד קצת סושיאל, נתחיל. אוקיי. Okay, so in the next 10 minutes or so, what we're going to do is we're going to describe what embedded build system or cross-build systems are. I did go over it several times, I'm not going to be very rigorous about it, but I'm going to give enough information to give us a framework to see what we're going to present in the next couple of meetups is meant for. We already know what cross-build chains are, so I'm not using it. I allowed myself to copy from myself, so this module is part of my embedded Linux training. Basically, almost every training that I give is related to Linux, but it has some specific additions that are about what DSCG devils is. Those of you who've been in one of my courses, it's usually what I demo on. It's not what I usually teach in courses, because the courses would usually be of the project or some other security-related who knows what, and then things are very, very specific. So this is general, and our objective within this build system is to give anyone who wants the tools to teach themselves how to be embedded Linux engineer. Okay? Our group is called Embedded Israel, but it's embedded everything. It's like embedded Linux, it's microcontrollers, it's you name it, and embedded Linux is a very important part of our curriculum. And because, first of all, because we can. And second of all, because we don't need to commit to like any vendor, hey, let's do something very like in, I believe, 99% of the microcontrollers. So this allows us to be objective and to say something that is like very, very, very right. And later on, I will show how the systems that we'll be talking about apply to all kinds of devices, whether they are x86, ARM, or RISC-V, and that's how we're going to work. So, when we talk about embedded Linux systems, the idea, let me just minimize this. Okay. So, the idea is to go ahead and do a very well-known and organized set of steps that allows something like software that runs on, or code that runs like on a host, on a system like mine, to run on something like this. Okay, so we need to somehow have source code and somehow make like this whole great shiny system, maybe whether it has like a GUI or not. So the idea is that we're going to take a host environment that we're going to prepare with the tools. In this case, it's in Ubuntu Linux, Ubuntu 23.04. We're going to tell some piece of code that is the build system what we want to achieve, and in a lot of like in my build system as well as in Yocto, what Yocto is open embedded. We call these recipes, okay? I think it also in Green River Linux back then, they also called it like that. And the idea is to use these recipes, this list of instructions, and create a system out of them, okay? So, the idea of most of embedded software development usually means that we have a build system that runs on, that has one architecture, and then we're going to do all kinds of things, process recipes, and have code that runs on another architecture usually, but not always. Why do I always say not these days? Because a significant part of the project that we built this day runs on ARM64 machines. And up until 3-4 years ago, most x86, 64, but now what product do we have that runs natively at ARM64 and is a laptop?
Apple Mac.
All of the Apple Silicon, yeah. And who uses all of the Apple Silicon?
Nobody.
Everyone. Nobody, everyone, or somewhere in between. The answer is always in between, right? Yeah, so this is, but regardless of that, we can reason and say, okay, so we have that, but it's like a Mac OS and run Apple's code and want to build Linux, so the libraries are not the same, the API is not the same, nothing is the same, okay? So the idea is to take a machine that is a host, it has all kind of source code, find recipes, and translate it into something that automatically and wonderfully works on the target. For that, we usually need to go ahead and use cross compilers. And when we use cross compilers, it's an embedded Linux. It's an embedded Linux group, so all of us know that already. It means that when we don't just do GCC or clang, because then the file will be, if we build something statically, built for the native target, and if we try to run it on the other one, it will say, hey, I cannot execute the binary file. But instead of that, we make sure that we take all the tools, all the libraries, all of everything, and cross-build it into the target. And I say cross-build and not just cross-compile, because it's cross tons of things. It's cross-building, it's cross-processing, it's cross-linking, and it's sort of cross-packing. Why do I say sort of cross-packing? Because we're going to take whatever we want and generate, which are the build artifacts, and somehow make them usually flashable or OTA-able, downloadable into our target devices. Okay? So I'm going to skip this one, but when we talk about building Linux systems, just like we covered with the bootstrap, usually there will be the following steps. We're going to go ahead and have source code of everything that we want, including the cross toolchain itself, and start from something. Something would be basic requirements of the system, like, hey, we want to have GCC of this version, we want to have Python of this version, and we want to have GNU make of that version, or CMake, or Gradle, or you name it, okay? So once we have these cross toolchains, and the cross allows us to go ahead and do GCC for another architecture, for example, we can build things like the Linux kernel, as we covered in previous meetups. I'm going very fast because some of the topics have been covered. But you can jump with questions if you missed one of the previous lectures, no problem. So we can go ahead and build it. We can build a bootloader, may it be Grab, Ubuntu, whatever. We can go ahead and take all kinds of packages. Now is good time. We can go ahead and get the source for XZ, right? XZ-utils, because now everybody's like going over it because there was like a huge vulnerability, yada yada yada, and we can build it from source. Okay, we can build a lot of other packages as well. Systemd as the unit framework. We can go ahead then, once we have like all kinds of packages, we can configure them. A lot of time with /configure, what is called the auto tools or automate. And we're going to build them with make. It can also be with CMake, it can be with Gradle, it can be with whatever. And then we can go ahead and pack those artifacts into packages, like dev packages, RPMs, or tarbles, or just with them as is. Okay? Another very important thing that my build system that I'm going to present doesn't take care of, but it could, is specifying licenses. Anybody who ever had a device in the market under their hands knows that they must provide software licenses. Is that correct or not? Of course it is correct. You absolutely have to do it. And everybody who uses Android or iOS or whatever can go ahead to somewhere in the settings and look for the licenses and see, oh, good, big file, and just ignore it and never open it again because it doesn't make any sense, right? So we specify the licenses, then we need to go ahead and create some images that we can somehow usually flash to the target, and that's it, we're done. So these steps happen always for every system, may it be Linux or not. Okay, when somebody goes ahead and makes a new version of macOS or of Windows or of Zephyr or of you name it, or of Integrity or VxWorks and QNX, no matter what, usually give you some package and say, okay, this is how you flash your target. This is how you do it. This is how you do software upload, right? So these steps happen always. There are no exceptions, no matter what operating systems, no matter if there is no operating system, because they have to happen always. And if anybody wants to prove me wrong, now is your time. Nobody wants to try. Of course I'm not wrong, but this is how it is, always. This is why it's worth talking about it for like 5 minutes. So, once we have that, great, we have a system. What do we want to do with it? We want to run it. So usually, especially if we do like a post-silicon verification, or if we want to do some sort of like a porting from one system that works to another system, yada yada yada, we need to have something running. So we usually are happy enough by just having something printed to a console via UART, and then we say, okay, we're game. Okay? So basically, once you have that, if you build a Linux system, you can say, hey, I have a sanity test that verifies that I can build a kernel and load something from some file system. It could be file system in RAM, and then they can do all kinds of things on top of that if they know how to do it. And this is what these first do. So when we have Debian put tons of like packages on top of like the init. Init forks all kind of processes, manage them if it's systemd or other thing, and start as processes, and everyone is happy. So we're going to start with something that is a little bit less fat and fancy, because we already covered Debian in a couple of minutes, meetups ago. All right. So what happens when I want to do these things? I'll demonstrate what I just talked about a little bit more graphically. What we have is a host that has all kinds of tools. The little boxes here are all kinds of emulators or VMs, okay? So you could run Android x86, which is the project I was part of over QEMU. You can run Windows over VirtualBox, you can run whatever. And you can run a real target that you can hold in your hands. So this fellow would be generate a package that would have things like kernel, all kind of turbo, perhaps for other microcontrollers that you have like on the board, or for who knows what. And it will have a kernel of some operating system. And now let's start talking only Linux, because the concepts are always the same concept. If we talk about Linux, it will have a Linux kernel, and on top of that it will have a root file system. Maybe it will have run disk, maybe no. Maybe it will have support for camera, or for audio, or for a proximity sensor, or for all kind of neural network processors, and maybe it will have nothing but UART. You don't know, okay? So it's up to you to know your target and know what to design to. So our first targets will be a couple of emulators. Why? Because of the reasons that I mentioned before. They're available, no commitment to any vendors, and they just represent everything that we need to represent, especially if we just want to get UART working, okay? So the next question after building would be, okay, I built something. How exactly these amazing build artifacts find their ways into the system itself? So this is usually called flashing, as I mentioned, and now we'll talk about a couple of alternatives for that, okay? So there are two phases, building and flashing. Building would usually include deciding what product I want to build. And from the same build system, usually I'll be able to build several products. Whether I want to build the exact same product, and this is intended for several different architectures, and I need to configure what the target architecture is, or whether I just want to add packages, remove packages, add features, and so on. I want one package for with debug information and with debug tools, and I want another package that is absolutely non-accessible whatsoever. You can only flash it with JLink or something. So when I say build 1 and build 2 here, what I mean, hey, these are build configurations, and it will generate the artifacts to whatever system. What happens in Android? Who has done AOSP development here? Our friend from the previous meetup now went back to Canada. So usually I would expect him to say hi, but he's done with Israel for now. So I am, okay? I represent us, thank you. And in Android you call a tool called launch to make all kind of like configurations, and then you call make. They have a GNU make wrapper, and on GNU make wrapper they just now, in the beginning they didn't even do that, translate all kind of make files to Ninja build system, and then they use the Ninja build system in order to build the AOSP code. And the output of this would be artifacts that would be all kind of image files. Okay. Same for other product and so on. It's not important. What happens with flashing? Like always, if I have some physical access and I can go ahead and convince the CPU, hey, you put this there, all is good. But there is like a well-defined protocol in the bootloader level that is called fastboot, and usually I'm going to go ahead and do fastboot flash. So what will I flash? The images that I generated previously. And then we have like this animation. Usually don't do anything with animation, right? But like, and then it takes some time, sometimes more, sometimes less, and we have things. Awesome. Same thing, another build system. Yocto project. The Yocto project uses a tool called bitbake. And at least half of the people here know that already because you do bitbake some target and then it automatically creates things for you. So what it creates for you usually be by default under the TMP whatever folder, and it usually be under temp, deploy, and so on. Okay? So it will create will be kernel, rootfs, and perhaps bootloader if you want to. So same, there is one thing for one target, one thing for another target, and how do you flash? Well, you need to figure out it depending on the target itself, because you need that. So the Yocto project has very strict definitions of what are the tasks, this is how we call it, that I want to accomplish. And tasks would usually have the name do underscore something, and that would be like do fetch, do compile, do package, do a sanity check, and so on and so forth. And doing everything together is going to be the Uber task that's called do build. Just for information, it's not a Yocto project class. Build root that some other people also said that they know. It is going to use a kbuild as the build system, which means doing all kind of configuration like the Linux kernel and then hitting a okay. So essentially, once we configure, we have something that is pretty much the same, but the artifacts will be under images. And here again, I can build like a kernel rootfs, I can build kernel rootfs, and I can build the entire set of Ubuntu tools, like the SPL that goes like to the ROM, to the SRAM, and the rest of like Ubuntu. So build root has the exact same steps, nothing new in it. And now comes the new system that we're going to start and cover, and how the layout looks like, and more or less how the tasks that we want to achieve will look like. And later on, depends how, if time will allow us, also how the partition label looks like. I will show it like on a live system perhaps, or I will unpackage the results. I'll start with unpackaging some of the flashable images, and in time we'll cover how everything was built, okay? So the idea here is that it's meant to create a common knowledge base for whoever wants to deal with embedded Linux without committing to learning how the Yocto project works. And the Yocto, I mean, I have motivation to say that the Yocto project is great because I'm one of like the recommended consultants. So they refer me to all kind of projects and I make good money and everybody's happy. However, this is what allows me to say that the Yocto project is very hard to learn. Very, very, very hard to learn. You need to learn a lot of things and you need a lot of experience to get to feel comfortable with it. Is this correct or not? Correct. Incorrect? Correct. Okay. It is right. I was expecting everybody to say no because you were smart, right? That's what the Americans would always say. You guys are smart. All right. Thank you. So, what I need for people to know here is just to be able to read passwords. And the rest of them, of the things, then I'll just either cover or answer questions. But when the code will be released, you will see all kinds of things. So the build system here, what it just needs to specify is a couple of environment variables before you start. Like one of them would be distro equals. Now there are two options for the distro from one of the previous meetup. It would be PSCG DevOS for Debian or Ubuntu, and PSCG BusyBox OS will be something that just uses BusyBox like on the RAM disk, and BusyBox and some other things on the Rich OS. What is a Rich OS? Rich OS would be something like Debian or something like that I would be expecting to load after an initial RAM disk did its part and wants you to switch root into something else, which is some of the things that we covered in the YouTube videos of the previous time. Did anybody get to see any of these videos?
I started to watch
Okay.
from the meetup descriptions.
Yeah, so I put them in the meetup description. So just for your information, basically, there are in youtube.com/@ronmunitz. There are some of the videos from the previous meetups, from the COVID time meetups, and the videos that I'm talking about right now are the list of Initram FS to happening, and they cover actually everything there is to know about what the Debian and Ubuntu Initram FS do. I mean everything, including absolutely everything, and this is why they take a little bit of time. Okay, but the important takeaway from them is that these systems will run an Initram FS that will be switch root to something that is like on your hard drive, for example. Okay? So when I say rich FS, rich operating system, I mean this, whatever is like on your hard drive. Okay? Alright. So, let's see. Okay. Fine, I apologize about this one. So for this we need to configure environment variables, and then we're just going to call a script called build image, and it will create all kind of what I call build artifacts. That will be an image that you can put like on a USB or attach to QEMU and flash it. There is like a flashing mechanism that runs from somewhere. It can run from a bootloader, but I actually run it from an Initram FS because this allows it to be much more flexible for educational needs. And the other thing that it will provide is all kind of images for performing over-the-air update installation. Okay. So the idea would be to build an image just like that with another tool. So if you saw the colors and more or less the flow, it looks the same as like in the Yocto project and build, and it does the same thing with an installer image. That's what I provide. And the Initram FS itself, as I mentioned before, will just go ahead and have some code of flashing. So this is not the most beautiful slide in the universe, but it's because it's well organized. So the idea of how we're going to flash in the AOSP, I'm not going back on because of the animation, but in the AOSP I had a slide that said, hey, we do fast flash, right? And here like we say, okay, flash something Initram FS. So the idea of how we do this Android's fast flash here is as follows. We have a bootloader. If we run on a real device, whatever bootloader there is over there, as long as it transfers ownership, not ownership, as long as it transfers control flow to a kernel that runs an Initram FS that we provide. Otherwise, if we have QEMU, we provide a parameter directly. This is the bootloader. Okay, -kernel -ini. Now here it goes. The flow of this Initram FS will check, hey, do we have a removable media? If yes, it will check if the label on the removable media is something that it expects, like PSCG installer. I mean, I just use the name because I just use the name. It enables it to grab. It can be motion installer. It doesn't matter. Okay. But this is the name. It is what it is. And if so, it will flash from this removable media to an eMMC or a hard drive or whatever else device. What devices are they? One can actually just enumerate whatever there is. Fair enough. It's perfect. Or one can provide it as kernel command line parameters, and I chose the latter. Another option that it will provide is to store some golden image. Golden image is something that you want to return to when everything goes really, really, really bad. So it's sometimes called recovery image, it's sometimes called the golden image, maybe it has some other name. The idea is that we will usually have some flow, for example, pressing some button combination, okay? Or having a command from user space like, hey, please do factory data, like in Android, for example, and it will reboot to a bootloader. In this case, again, I implemented in the Initram for reasons we'll explain later, because bootloader needs to be very specific and needs to understand, which is more generic. And once it's there, the idea is that this recovery, it will be using something that has been flashed by removable media into a very particular place in the persistent storage, like in the eMMC or hard drive. This particular thing in the current design. It's just a partition with a very specific label. Okay? It's called recovery. And then it would have a recovery tarball that we will be able to extract it and somehow automatically flash everything to the right places. The last thing, and there is a P missing here, is an OTA over here, SW update, software update. Which means, hey, I have a server that I trust. I want to go ahead and from this server that I trust, I want to get a tarball or whatever. I want to get it into my device and then I want to flash it somewhere. So a richer OS which will access this server, that will access the network, that if it's rich enough and we have proper chain of trust and certificate sets and all these things, then it will download everything, verify everything, say, okay, I trust everything that I have, and then it will reboot to a system that can actually flash. Why it will not do it itself? Because you don't do operations on the root file system that you're active. Now I can go ahead and ask all kind of riddles. Why also you don't do it? Because what if you want to replace init and then not running? But there are other reasons as well. Okay. So these are the things that will happen, and some of the tools that some of them, how we build them, are in the YouTube channel as well. Would actually make sure that like we can resize the file systems to take whatever size we want. So some of you like know Raspberry Pi will notice that on the first boot it will say, hey, resizing the file system to take, and then instead of like 2 gig image or 1 meg image or whatever, it can go ahead and be 32 gigs of your SD card. Because it does resize to FS and does these things. So we also do these things. We also check that the images that we have are correct. And we set up all kind of partitioning images, partitioning schemes that don't have too many requirements. The only requirements that are important, and they can be customizable in one line of code, is that the root file system that we want to use as the rich operating system needs to be called system. Not asking for much. Anybody wants to guess why I want to call it precisely system?
You should have a link to it, so it's you took this name.
I actually don't. It's a good assumption. I actually don't. The reason for that is because this is the name of the rich OS partition in Android, and I usually use this kind of like operating systems before explaining a lot about Android and a lot like very lengthy courses that took months, okay, for some research, security research, or before talking about your project. And so a lot of the variable names that I'll be using will be some mixtures of both of them, which is actually a good time to say that when the code is published, there is a good chance that there will be changes in the variable names. Because I just built it like in the last couple of like more seriously in the last couple of weeks. I assumed it would take me a couple of days. Of course, it took me much more, and I didn't rename everything. Okay, there are a lot of factors. Okay, so these are the flows. Removable media, yeah, okay. OTA update, yeah, okay. No, run this just switch roots to the operational system, and that's it, and we're done. So, just like the other operating systems, like distros, like distro build and build root, also this reference system fetches, configures, compiles, and packages, and so on. But it also shows all kinds of important trade-offs in build. Like, hey, I don't want to download everything all over again. What do? I want to force download. This is the fetching part. I'll just use some caches. Okay. Now in Yocto project, you have two kinds of caches. Anybody want to remind me? One start with D and one start with S. We have the downloads dir in Yocto project where S-state cache. Yeah, that's the other one. So the downloads dir will just get the tarballs with wget or curl or whatever, and it will also get the it will get repositories. I was like because I was going to say it will get the Git repositories, but it can get SVN, it can get whatever you want. So we'll have them under a folder that if you put your build configuration to point to it, and the tarballs already exist, and the digest for them it matches whatever the recipe's state, then they will not be re-downloaded. So you can do it on offline, and everybody's happy. The other thing, if you want to go ahead and reuse the state of a previous build, so you don't need to rebuild everything again, then there is a cache managing system in a folder that is referred to as the state cache clear. So here I did some things a little bit similar, mostly for reasons of Debian packaging and the bootstrap, so that we don't need to call the bootstrap all over again, or we need to call the bootstrap if something has changed. So I will mention all kinds of constraints whenever and considerations that one needs to do to handle all kinds of trade-offs. One of the trade-offs, as I mentioned in one of the previous talks, would be, hey, if I never want to do any software update, I don't need any caches of the Debians. Why do I need 100 or 200 or 400 of megabytes of caches for packages that they're already installed? So what do I need for? So this is one thing. Another thing would be, hey, I want to put the code that actually gets a package, an OTA tarball from some server. So I want to take care of that. Some other thing can be, what do I do? This is now we'll respect the place. Maybe you already solved this, but like, what do I do when we have like when we want to have a read-only system, but I still need to write to all kinds of places. So there are all kinds of strategies. Do I want to just make some volatile temp-fs? Do I want to use overlays? What do I want to do? And so on and so forth. Now this build system now will be used to build Linux, but it's just pass-through. So it's configured carefully, it can build everything. So we're good with time so far. And so the summary of what we've done, we gave a description of a couple of like embedded build systems and talked about a little bit about like cross-building, not cross-building. I skipped it very fast. So took care of looking at a couple of build systems, including introducing one. And so are there any questions to start seeing an example? I said we're going to do it until 8:30, but I'm happy to stay a little bit more, and the conversation will continue this way or another. Are there any questions so far?
What about target system, bridge system? Did you saw like Alpine Linux that used in the embedded system more than Debian or other distributions? So and there is bootstraps for that, and seems like it's very similar to what you're building.
Of course, every build system works the same. So if you don't need to do boot, you can use like the Alpine package manager and do this kind of thing. What I'm saying that with this build system is that I have two variants in the Linux part. Linux and Debian and Ubuntu, for me they're the same, and a rich file system that runs BusyBox. But if you guys remind me, I will do an Alpine OS implementation. It will to do something simple enough and not starting customizing like just do something that would say we have like UR. I suppose it will take me 5 minutes. Out of them, 4 would be doing the copy paste from one folder to another folder and modifying the variable. Once I have init, I don't care about anything. It all is the same. So we'll start exploring how this build OS. I don't have a name for it yet, to be honest. CCG demos because I always demonstrated with Debian or Ubuntu, but now I don't. We'll show quickly how it builds a Linux kernel on round disk and BusyBox OS, and then I'll leave it up to you to tell me if we want to start looking at the builder now or do it at another time. We can just start and okay. So let me quickly go to the command line. Okay, this is an example of the system trying to do an OTA update. It's already running, okay? And the reason why I cannot do it is because I didn't get a server. This is one reason.
Yes,
and the other one, yeah, sure. And the other one is that I don't have an IP. Now, what I want to show you here is not what the code does or not does. Let me just get it so we avoid. Okay. So this is my root file system, and you can see here that it doesn't have an init script. What you can also see is that there is an SBin init code in it that points to BusyBox. What I can tell you is that system has gone through a switch root statement, okay, to run this. And I will show it to you when I cover to run this, but I don't think that it will be today. Now this rich file system, if I look at it, this is a partition scheme that I have here. We can see SDB1 that has the label PSCG installed, which will be the removable media, which means that if I boot into it, it will try to flash my system. And it has all kind of partitioning that wants to mostly support AV update, mean okay, I have a system that is running now, I got another system that I want to flash. Let's go ahead and flash it, but let's do our best to not ruin the currently running system. So there are all kind of partitions for configuration that's supported. You use the words OK state for keeping state on it, but usually state will be kept with some common partition to the bootloader and to the rich OS. In Android, this is our identity, for example. And extract will be a place to extract an OTA tarball if I want to use it. Now, this particular system, it runs on a system that's on a partition that is labeled system, okay? And if I look, for example, now where I am, this does not queue. Then I will see, hey, this is an overlay FS. So one of the concepts that will be seen is, for example, what it is exactly. What does it mean if I want to go ahead and use a read-only file system, like this system partition? I just designed it so I know it is. And I want to write over it without changing any file. So the idea will be to overlay some writable device, and this is what I put to right now. Be like, hey, this is like overlay FS here. It means I'm overlaying the upper directory that is in some place over a system directory. So if I went ahead and did something like mount label equals system and then n, I need to mount it as read only because it wouldn't let me, because it's already been mounted, okay? It's going to say cannot open block date. It's a sign to show it another time. Okay, anyway, if I want to go ahead and show that, I just want to show it another example of several things that we're going to do here. So if I'm going to get rid of like an overlay FS here and do the March meetup, then we'll see the exact same thing. We don't worry about the not found. It's been like I added to it later, and it's something that is writable. We're going to see that the file system is dev SDA5, and this is like what we run. Now what we run here is exactly the same thing, and it's BusyBox related, okay? And if I wanted to go ahead and, for example, allow an installer then I could go ahead and run a code that looks completely different. So it's going to say, this is like a light, we maybe I will put a LED or some note, and it's going to say, hey, I'm going to go and flash some things, I'm going to do FSCK, I'm going to do resizing of partitions, and I'm going to do everything that like a flasher does, okay? And then if all is good, I'm going to say, hey, I'm done. So if I do that, and I added in the system some, it's not breakpoint, it's some stop points. Via kernel command line, hey, you can stop here, or you can stop there. Then I will see that the run list that I have is also a BusyBox, okay? So if I see like which is shell, it will tell me bin sh, and which is this guy, and it will say, okay, it's bin sh, BusyBox, and so on and so forth. And if I wanted to see what are the things that I provided to it, I will see that I mounted SDB1 onto media removable. And if I look at block ID, I can see that this is something with the label PSCG installed. And if I go onto it, I'm going like this because we're going to recap very soon. We'll continue with the build system another time. If I'm going to go to this mounted directory, where was it? Media removable. A little bigger. Then we can see that we have all kinds of things like manifests to tell us, hey, this is the version that I had, or if I want to use the same thing for OTA, this is how it looks like. This is like the size of it. This is a tarball that I would get. Like I have a mechanism that uses the same tarball, put it on the installer media, and then I can design a flasher that does recovery, installation from media, and over-the-air update with more or less the same code, just a little bit different parameters. So I have all kind of things like that, which is okay. And what I also have is installables and ext4 images, and over there I have like a system image. That if I go ahead and do mount, I think I just needed to look. This was the problem I had before. System image to temp an image. Then I will see that it looks pretty much the same. Okay, whatever I have there. So this is the system image that I have that I mounted, and it looks pretty much exactly like the BusyBox version. Image. So here we can see again that we have like bin and BusyBox, and it looks the same. Other things that we have, got the name page. We can see that we have these things. For my current system, I have an etc release file. Usually you would have like in Debian OS -release. So I put some word in it in the unit parameters system, and on the other one, I also gave it the name root test. So the idea here is that I will use for the BusyBox operating system the exact same code to create both an init parameters and operational system. I will put a client code for an over-the-air update system on the rich operating system, and then we will use it to do over-the-air update to a richer OS that is a Debian file system. But that will happen in a couple of weeks from now. Okay. So this is the beginning of like what we're going to do, what the build system is, and I think it's a good time to wrap it up, unless you want to a teaser of like how the build system looks like. Teaser or not?
Teaser.
All right. So let's do it quickly. I'm just going to get out of here, and I should have Visual Code somewhere here. Okay, so there should be. Can you? Is it clear enough, or should I put it and make it bigger?
It's too wide.
Huh?
Too wide.
And too wide. That's yeah. I'll just scroll. That's okay. So the idea here is that we start with just a shell script. It's called build image. That will call free function, and that's it. We're done. So it initializes some environment to read some files. It prompts a user to say, hey, like, are you sure you want to delete all the folders if it selected some configuration values for that or not? And then it will select a distro out of a set of ready distros and aiming to do all kinds of instructions over there and build them. So I will show quickly how we done like this one, but the beginning is like this. We go ahead if the user provides a config file. This is how the next lecture will look like. We're just going to go over the code, okay? Because all the concept I already gave them. So if there's a config file, we're going to look at it and then once that's a config file, we're going to have our build intermediates under a particular directory like everywhere else, and we're going to be expect, before calling this script, somebody to set a distro variable. And the distro variable, I'll show it soon enough, will go to a particular folder and source all kind of configuration files from there. You will have tons of like .build config files throughout the system, which will define, hey, I want these packages, I want this kind of fruit file system. If I want to add Alpine to it, then a distro could be PSG Alpine OS, and then it will do that. And I have to do it in the next couple of days and show it. And then we're going to go ahead and show what is like the build configuration for this guy. If they decided to remove previous build, either the entire build folder for several products or a specific product, then we're going to let go of that. And just it's going to call according to whatever has been sourced. It's going to go ahead to a folder called distro-dir, see the distro that has been selected, and then it will just go ahead and call build distro.sh. We're currently, and the distro needs to start like with the word PSD. So if I want to go ahead, and now it will not be white, and look at the distros. I have here two distros, one called PSG BusyBox and the other one is Debian, that try to share whatever they can with a common Linux distro. And the common Linux distro, and I will not go over all of it, has configuration files. You will have in several folders config underscore something, then underscore all kind of like variables to have to namespace the configuration files, okay? So it will be clear. The importance here is that things are simple enough and clear enough. So we'll say all kind of things. For example, which extra layers you want to add, where we want to have like the installables or the work here for where we're going to work on the root file system or the kernel and so on, and where we want to go ahead and put like the final images and so on, okay? This is one thing. The other thing would be just running like this main build distro, and it uses some sort of polymorphism because it sources other files according to the distro. But for the common ones, it's just going to go and set ARC related variables if needed, is in these cases because it's a little bit of a hack to be able to deal with the differences between the Debian, the way the Debian calls the repositories, and what ARC command returns, or like arc-m or a unim-m or ARC. Okay? So what we do here is say, okay, these are the tasks that we want to do. If we want to build the rootfs, and you know tasks for both like the Yotta project and build root, then I'm going to go ahead and do a pass before I build everything. For example, if I want to bootstrap it, or in the BusyBox OS case, if I want to just copy BusyBox code, build it, and just copy it once for the init run fest, and twice for the second time for the rich root fest. If I want to do that, then I do a pre-pass, and after I do everything, I will add layer to the other thing. What is everything? Building a kernel and perhaps installing loadable kernel modules. Because if I want to install kernel loadable modules to a root file system that I'm using, I need to know what the root file system needs to exist before. Okay, so we do this pass. We build the kernel. I'm not even going over it so far. We build the initial RAM disk, and then we add all kind of layers in the rootfs, and we're done. An example in the BusyBox distro would be this, and this will conclude for now. So first of all, configuration-wise, it doesn't show much. It doesn't show anything really. It just goes and sources the common Linux definition. Right? The Debian one will start defining variables like, hey, do I want Debian, Ubuntu, and which version does it? The other thing here, sorry. Build distro. So it will do very simple things. And this quick demonstration thing, usually in real build system, you will have a layer or recipe and add it. But this is done exactly as it's meant here, like a quick demonstration. So we do several things in the common steps, and I want to quickly go over them, and the comments say a lot about them. So the first one would be, I need to look for the pre something. Yeah. Build rootfs pre-pass. So it calls the Swiss knife. The Swiss knife is a configuration variable. As far as you're concerned, it's BusyBox. It could be Toybox, it could be Toolbox, it could be something you build with Rust or I don't know what that knows how to do ls, ps, mount, and so on. So assume this is BusyBox, okay? And that here we build BusyBox. When we're done, we're going to go ahead and just copy whatever we did in BusyBox. There is another term that I'm skipping right now. That means building the entire round list and then using this as the root test. We're going to use the entire BusyBox right here. So how do we do like this copying? It's not so complex. I have a folder that starts with BusyBox installation, and I need to prepare a couple of folders like proxies, dev, and temp, because I will want to mount them, and then we'll move the mount before I do switch root. Okay, so I must have them. So these are some things that we define here, and that's fine. Then, this is common, the building of the round disk and the kernel, it's common, it's completely common. And after building this, and already having like the BusyBox and these folders, I have a post step as well, a post pass. Sorry, add layer pass, because I do it, a post pass is for things like cleaning caches and so on. So what we have in the add layers is something that just calls adding init tab and the version. You saw like version and dashboard fs. So that's what it is. I don't know why it doesn't. Ah, okay. So here it is. I'm going to add it like to the rootfs dir that I planned, and here I echo the date and dashboard fs to the root file system. And the other thing that I do here is update xe init tab. Why? Because if I have this file with BusyBox, then it will automatically run some of the commands here, passively respond them, and so on. So what do I do here? There are some run levels. Here I do sysinit bin echo this colorful message. It will do it. Respawn shell. Okay. This minus means that you will not have this annoying no TTY, cannot do job control message. Okay, no control TTY. And here there are a couple of things that you see what happens before. Here, if I prepare it, there is a script that automatically does DHCP. So if I add a system that has this, then I will have the IP set already. And here I have like automatically having like the OTA update. Now because the system I started showing you, it's part of the example, I just going to show a little bit more for. And because the system I showed you doesn't have like the DHCP, then the OTA complain, hey, I can't download. So this is an example for a root file system. And the other things are pretty much similar to what we saw in one of the previous meetups. I just want to remind you that had like the fetch BusyBox and kernel create initial RAM disk, kernel tarball, build kernel build modules, but much more configurable. Okay, so just to recap, what we covered here is the common objectives of build systems, and starting to prove, showing what mechanisms for like that are extra for whatever the other builds prepare. Like, hey, I'm going to show you how to do entire flashing endpoints. I will prepare it. Our TA will be prepared. Our recovery will be prepared. And I just showed you something that creates like the root file system that we'll be using, because for the demos we've seen the previous time, we were just using RAM-disk. And now we'll use RAM-disk because I need it from fast, and use flashable contents in order to do a root file system. So we'll play with some things, and let's do fast forward. If one system works, if this simple BusyBox OS works, that doesn't do anything, works, and you know how to create other files, other root file systems like Alpine, like Debian, like Red Hat, like whatever, like Android. Android is a super valid use case here. Then you can just replace the code in this partition, switch root to that, and then you're done. And by the way, this is what we've done in the Android x86 project of over a decade ago. We had Linux, we had kernel running, and then we did switch root to an Android init, and then we're done. So that's it for now. If there are any questions or requests for the next time, I'm happy to take them.
What about device tree and special tools to make drivers, for example, before we compiling the BusyBox or something like that?
So in this particular case, this is a very good question. They will be discussed when we talk about building the kernel and about specific devices. For x86 devices, there are no device trees really. For our RISC-V, what we're going to do at the beginning for the demonstration, before showing the real devices, which of course we will, what we're going to do is dump the current device tree that is like on the emulator. The thing is that the emulator hides it from you. Because if you run emulators, at least now, in the past, you had to add device trees also for ARM emulators. But now, for the QEMU target of the kernel, basically recent QEMUs, I think from 6 and on, they just give you device tree already. The bootloader can completely populate the device tree for you, and the kernel will be happy for you. So what we're going to do, we're going to cheat. We're going to dump the device tree from a live device, and we're going to copy it, and then we're going to use it. This is what I do, like in my training when I want to teach about like doing network boot with a TFTP and later with NFS. Sometimes yes, sometimes no. Then we also show how we take like a device tree and how we like populate them. Okay. So this is it for now. It's a little soon, but there's still a couple of places. Next courses that I will be teaching in Israel would be Yocto project on this April 11, April 8th to April 11th, and then I need to fly to the United States. And then next internals in June. But in the past, people could be admitted to it without being really good with embedded Linux or Linux kernel, and now no, because Android got super complex, and there's like you need to have a lot of background materials if you want to be in this course. But anyway, you have some details here, and like a discount code if you want to, either you or people from your work to register and take the course. And of course, if you come a couple of people from the same place, you'll get a much bigger discount. As I always say in the group, I'm happy to do it as long as it sort of organizes itself. This is why I usually do invited courses. Hey, can you teach here and there? Yes. Easy, yes. Not easy, no. I don't do public courses so much, but sometimes I do. Okay, so thank you for listening to this. We will continue soon, and I will publish mostly in the Facebook group, like when we do like the next session, because it's very probable that the next session of this one will be online. Okay. And I will go over every single line of code over there, and more than that, I will actually ask some of you to go and help actually. I mean, it's pretty much baked, it's pretty much done, but this will be part of like our common like community training. This is what I was hoping to achieve with the afternoon meetups, like to have like enough time. Yeah, so that's all. So thank you very much for listening, and please continue enjoying the drinks and the food. And thank you. Let's talk.